In that previous slide, the green protons that are shown, it kind of looks like they are just behaving independently of one another, as if it's just a collection of free hydrogen atoms roaming around. But in organic molecules, the hydrogens don't roam freely. They are attached to carbon or to oxygen. They're part of some molecular structure. And it turns out that the resonance behavior of hydrogens will depend very strongly on what their environment is. Is the hydrogen part of a methyl group attached to carbon, or is it perhaps a alcohol hydrogen attached to an oxygen? Those kind of details are great to be able to figure out when you're studying organic compounds, and NMR is a good way to see those differences. And it turns out that this TMS is chosen as a standard, not only because it's available and stable as a molecule, but when we compare its behavior to other molecules, we find that these hydrogens in these methyl groups here, they're shielded from the external magnet, shielded by the electrons that are surrounding those hydrogens. And so that affects the magnetic field strength that corresponds to a certain radio frequency. So if we've got a magnet of a constant magnetic field strength, then we're saying here that it might take 200 megahertz worth of radio frequency to stimulate or resonate those particular hydrogens. And it turns out that it's going to take a higher radio frequency to do that same thing for other hydrogens and other molecules, because they're not as shielded from that magnet due to their environment. And that leads into this idea of chemical shift. And we're going to see some graphs showing NMR results, and the horizontal axis is always this chemical shift. That's a small Greek letter delta up at the top. And you can see how it's defined here. We're again comparing everything to this TMS. If we were, as it says here, to take chloroform as an example, the hydrogen in that chloroform, because it's attached to a carbon that also has those chlorines are pulling electron density. It's pulling electrons towards themselves. So the hydrogen doesn't have as much of an electron cloud around it, if you will. The hydrogen's a little more naked. It's a little more exposed to that big magnet that this thing is sitting in the middle of. And so as it says here, it takes higher energy, higher frequency to cause the hydrogen in chloroform to resonate. 1456 higher than the corresponding frequency that we would need for that TMS standard. And so as you can see down here, what we do is we're comparing what that frequency would be for chloroform, subtracting away this kind of the standard frequency that our standard TMS would require. And because those numbers of hertz are so large, what we do is calculate this as a parts per million. Just like percent is part per hundred, parts per million works in a similar fashion. At the top we would just have the 1456, the difference in those numbers, and we divide it by the radio frequency that's again needed for the TMS. And then we multiply that by 1,000,000, or 10 to the 6th. And what that does is give us chemical shifts that tend to be between 0 for TMS and about 11 or 12. So we get a nice little scale of numbers that makes it easy to compare. Again, ppm is parts per million, so that's just reminding us of how it's calculated. And these are generally measured to 2 decimal places like you see here. Sometimes you see the little delta in front of that 7.28 to kind of indicate what it is a measurement of, and that is uniquely characteristic of chloroform. Only the hydrogen in chloroform would give this particular resonance. At least it's very unlikely that another molecule would match that exact number. So we call this the chemical shift because, again, we're comparing how much the resonance frequency is shifted for chloroform versus our standard. And as it says at the bottom, what's nice is we don't have to worry about this calculation for every particular hydrogen we're interested in. We're just going to talk about what kind of chemical shifts have already been measured and how that, again, is characteristic of the environment of that hydrogen. That's really what's useful about this. NMR is usually a matter of getting a graph. Sometimes the graph is described, other times you see it actually pictured, and this is the NMR spectrum for chloroform. Again, the H1 is reminding us that we are analyzing the hydrogen atoms. You can do NMR on other atoms, different nucleuses. We're going to talk about carbon-13 a little bit in a few slides, but hydrogen is the atom of choice in most of the time. So notice the chemical shift down here. It's kind of strange. We put the 0 mark on the right. That's just the way it's always been done. And there's not a peak here, but sometimes you do see a little peak at 0.0 because that TMS can be added as a standard just to help calibrate the instrument. And the only peak, the only signal we're seeing for chloroform here is due to its only hydrogen. And notice it's at 7.28 on this scale. So again, we're placing that with other compounds with different hydrogens would produce other peaks, sometimes several peaks, but they tend to have their own unique chemical shift. So if we know for a given chemical shift what type of hydrogen to associate it with, that helps us a good deal. A little bit of terminology here. We talk about the hydrogen resonating in chloroform that is downfield from TMS. That corresponds to being towards the left on the graph here. Again, it's higher frequency because these hydrogens in things like chloroform are not as shielded from the magnetic field. The electronegative atoms like the chlorines, again, pull electron density away from that hydrogen, so it's said to be de-shielded, or there's decreased shielding compared to TMS. And again, here's the opposite terms. Signals that are upfield from chloroform would be at lower chemical shift, closer to the measurement for TMS. And although you can have negative chemical shifts, we won't encounter any of them. Most all important organic compounds have chemical shifts that would put them in the positive range, that would make them downfield from TMS, in other words.